It's a long title. Okay, thanks for the acceptance for the invitation. It's I prepared this. Excuse me. I guess so. Should put closer here. Yes. Okay. Well, I prepared. This is a short talk, so I want to make it really short. This is a problem that I more or less stumbled on this problem, and we did some experiments, and we found something interesting about this thing. Random walks is a very are very well known. You know, pretty much everything that fluctuates you can more or less model as a random walk. So it's surprising that you can find some new features of random walk somehow, some structural thing that is new. So I'm gonna try to show you. Well, first we need to understand what is the longest increasing subsequence. If you have a subsequence of numbers, for instance, any kind of object that can be ordered, you can, and you have a sequence of these things, you can ask for an increasing subsequence of this series. So it is a subsequence within the sequence that has maximum length. This is, I have a sequence like this, I have a subsequence in which each element of the subsequence is ordered. This can be, here there is a minor detail, it can be strictly increasing or not. So here it's non-strictly increasing because it's less than or equal. And the indexes are ordered. So I picked a sequence and found a subsequence. We are going to have some pictures. You're going to understand it better. This is a very ubiquitous, this is a very common problem in computer science for applications in general. For instance, in bioinformatics, you want to align gene sequences, and this is a problem of finding common subsequences. But finding a common subsequence is the same thing as finding an increasing subsequence. You just order one of them and look for that order one in the other. So this is the same problem, in fact. Computational linguistics is this diff that we have in Unix. You pick two files and give a diff. It's the core of the algorithm is running increasing subsequence finding thing. And statistical process control, because this increasing subsequence can be used as a trend marker for any kind of time-independent process, can be even finance or whatever. But we are more interested in the basic properties of this thing. And it's the complexity of giving a sequence you find an increasing subsequence is something that you can do algorithmically in order and log n. So this is not a very hard problem. The classical list problem, however, is a very interesting problem. It's in the core of most spectacular developments in mathematical physics in the last 40 years. So Stanislaw Ulam, was apparently interested in the sorting of bridge hands because he was a heavy player of bridge. And he posed this question as one possible question to be solved by the Monte Carlo method, with which he championed it also. So he asked, how does the length of the longest increased subsequence of a random permutation grow with n? And it took nearly 40 years to solve this problem completely, using an assortment of techniques. It started with the representation theory of permutation groups, nonlinear field theories, integrable models, then interacting particle systems, the asymmetric exclusion process, whatever you can imagine, lax pairs, you name it, has been used to deal with this problem, till finally in the end of the 90s, these guys at Courant found that the length of the increasing subsequence of random permutations is distributed like this, where this variable is Tracy-Widom beta equal to 2 distribution. So everything is connected. It's a very interesting problem. But I don't want to talk about this because, first, because I don't know much, and second, because it's not our business here. Recently, but 2 or 3 years ago, some guys, these guys here, asked a very simple question. What is the length, what is the behavior of the length of the longest increasing subsequence of a random walk? So a random walk is this object. You make a sequence of subsequences. This is pretty much a time series of the position of the walker, S1, S2, ST. So this is a sequence of numbers. They are correlated. This is important because it's not that easy to deal with correlated random variables. And how does the length of the list of this random walk scales with n? It's surprising that it takes this much time to be asked this question. So what happens is that it seems that this problem is really something new. Nobody looked at it, at least not explicitly. Nobody looked at it. Probably the literature is so huge of random walks that if you dig a lot, not a little bit, you'll not find much. But if you really go after this thing, you will find one or another result lost in some operations research paper, reliability. There are things like this. It's very different from, for instance, the structure of records, the structure of range, these other more common things about random walks. You know a lot. And developments have been very large recently. But this list thing is not. So what are the known results on the list of random walks? This basically two preprints. One from 14, one from 15. The guys showed that if the distribution of step lengths are of finite variance, it can be finite because it just normalizes. Okay, they put one here, but whatever. Then the expected value, the first moment of this distribution, obeys these bounds. So this says that it's bounded below by square root and above by square root plus an or, is a little O term that they don't know what to do. And these guys, and they are, serious mathematicians, okay? They state it explicitly in the paper. They say it's not immediate how to do any better. First, the guys can't get the full distribution. It's not their business. They don't do this usually, and they can't, in fact. They can't even go to the second moment for random walks of finite variance. And the other result that followed 2 years later, also by Pérez and Pimento, also this very competent mathematicians, they proved that if the random walk is composed of step increments of infinite variance, then the exponents change a little bit. They become larger. So you will expect larger, longer increasing subsequences for random walks in which the step increments are of infinite variance. And these bounds are non-sharp. They are not sharp. And they come from some kind of renormalization. It's a kind of real space renormalization. It's some renewal arguments also. There's a calculation. It's possible to read more or less this paper, in fact. Yeah, it's hard. Because these guys write papers of 75 pages every 2 weeks. And this paper, these preprints, this subject is so different, you know, that the first preprint has 6 pages and this one has maybe 10. You're going to see in the end, they have been published, you're going to see the page range is some 6 pages in small format. So it's just some calculations, really. And they say it's not immediate how to do any better. So what did I do? They can do the calculations. I can't either. So I put this in the computer to try to figure out what we can see. And I did some numerical experiments, which is the main report here. I simulated the long random walks, symmetric, for several different distributions of finite variance and of infinite variance. These two here, in fact, don't have even the first moment. It's a Cauchy and a very heavy-tailed distribution. And they are long, up to 100 million steps, and sampled a lot to have good statistics. 10,000 samples of each one, and they now calculated the least and accumulated this as a histogram. And I measure simply the first and second moments of this thing. What I have here, this is a picture of what we are looking at. Okay, this is a 1,000 steps random walk with normal distributed step lengths. So you can see this 1,000 here is more or less square root of 1,000. Here is a Cauchy 1,000. Here is 1,000. Also, it is a Cauchy random walk. That one is a normal random walk. And then we look at the points which, when put together, form the longest increase subsequence, because there can be many. Okay, this is one of them. The number of longest increase subsequences is an open problem. It's hard to calculate. It's not a trivial combinatorial thing that you do in 10 pages. The number, how many? Okay, I found that this one on top, I believe it's 89. The length of the long, this is, so okay, how many longest subsequences are there? We don't know. I see. So this is what we are looking for. Here is how the first moment scales, the average, the variance, and so they scale pretty much in the same way, you know. This goes like this goes like this, and if you look at all distributions, we found that the exponents are the same for the first moment, second moment, third, you know. And this suggests that the scaling function, the PDF of this thing is something like this. Because then you integrate this, calculate the pth moment, it's going to be like this. It's just a change of variables, okay? So and then we test these ansatz for this kind of distribution, which has been seen before many times in random walk problems, general with a square root of n. And it is like this. So for all distributions of step lengths, heavy-tailed or not, that scaling form is obeyed, but with a detail. There is a detail on this. When the step lengths are of finite variance, uniform, Laplace, and Gaussian, this exponent here, this half here, they are all equal. They are kind of universal, and the distribution function is universal also. When you have heavy tails, this isn't true anymore. So there is a dependence on this theta with the heaviness of the distribution. This is, we don't know how is it. We don't have any analytical form. These guys, mathematicians, don't have either. So we just verified in numerical that there is some scaling that is universal for finite variance, non-universal for non-finite variance. And we went a little bit further. This rigorous bound, it doesn't preclude this little o term can be a logarithmic correction. So it can be like this. Indeed, our data revealed an intriguing linear relation like this. Why is this intriguing? Because of the b. I wasn't expecting a b here. Okay, so this is a second order. This comes from second order. And then we do a fit. I'm in my last slide. We did a fit like this, supposing that from the b, it's 1/2. I put this 1/2 here. Well, here we are entering the realm of wishful science, you know. So because it's double ln of ln, you need some 10 billion points to do something that is worth. But in any case, 100 million is enough. Is good. And I found these constants, and we then conjectured that the true asymptotics, it's a lower bound square root of n, an upper bound square root of n plus some small epsilon term, that the true asymptotics is like this. And this pushes the asymptotics by an ln factor that the mathematicians were very surprised to find, because this is found in the discrete random walk, in the simple random walk, plus minus, on z, not on r, not on the real line. And I also, slightly boldly, put this lower order terms here. And the constants are a little more than numerology, okay? They're close, but we don't know. In Mauro, I put an exclamation mark here, you know. Everything that Physical Review doesn't let us do, put an exclamation mark and say that this has been obtained for the first time. So in one slide, I did both. And that's it. So we need to revisit this simple and lazy random walks, because this is easy to solve. And in fact, for step lengths of size 1, the least is the range, which is the record. The range, and if you pick an excursion that is always conditioned to be positive, it's the record of this thing. So this can be done, but this is not very interesting. This is interesting, because for this, there are very few results. The structure of records and range of these things, it's a nasty problem. The combinatorics look ugly, you know, some trinomial, non-symmetric coefficients. It's not funny. And explore these dependencies for the heavy-tailed distributions numerically. So how does this approach the upper bound of Paris and Penmantel? And for 2 dimensions, it's even worse. Okay, nobody knows everything. These are pretty much the entire literature in this field so far. It's less than the number of papers of Carlo Maggi, you know. So it's the entire field. It has less papers than one guy. And they are all very new. It's this, and this one was my contribution. And there are many things to do. I took pause on this problem to try to do something more analytical on this here. Excuse me. Here on this thing. Then to try to, I know, have a dent on this. Okay? Thanks.
Some results, and it's mainly regarding how evolution